All right, you're good to go.
I couldn't unmute myself with my screen shared. All right, so hi, I'm Joey, and my project for MIT Think was creating an open source modular food packaging robot using food safe 3D printing and computer numerical control for disaster relief. And as we know from the past trends of climate change, natural disasters aren't going anywhere anytime soon. In fact, it's estimated that natural disasters cause $210 billion in damage worldwide annually. In the United States in 2020 alone, over 1.7 million people were displaced. Now, there are various organizations that dedicate relief efforts to natural disasters, and one of these is IDES, the International Disaster Emergency Service. And I've picked this organization over others like the Red Cross or Salvation Army because I've actually participated in their meal packing programs. So this is an organization that I have experience with and I want to help out. But IDES also does other activities, such as building sheds for families to store their belongings in after their homes are destroyed in natural disasters. They also send teams out to affected areas to help directly. Now, one thing is the meal packing process. It's a very repetitive task. It takes like hours of doing the same task over and over to pack how many ever meals you're making, which is generally on the scale of thousands for one day. So I was thinking, if that process could be replaced with a robot, volunteers could better spend their times doing activities that only humans can accomplish. So what would one of these machines look like? Sorry, this is the flow chart for the packing process. First, you have to pick up the bag, put it under the funnel, add the ingredients one at a time, remove the bag, and this is the largest bottleneck in the process is weighing the bag and correcting the weight. So you have to add or take out rice to make it weigh exactly 14 ounces so that it can be shipped. Then it has to be moved to the sealer, sealed, and then put into the cardboard box to prepare it for shipping. But with the robot, we can eliminate a lot of these steps. There's a lot less movement. All the ingredients can be added at once, and it'll be a lot faster. And you can just weigh the bag as the last step, just for quality control, although the bag should weigh this exact same every single time. So now, what would one of these machines look like? So this is an industry standard machine called the RBFA6, which can package various ingredients in plastic pouches at dozens of cycles per minute. Although the slight problem that IDES isn't using this machine is these can cost upwards of $65,000. And that's a problem for many of these nonprofit organizations. So I wanted to create a much cheaper machine with a much cooler name. So I don't think I've ever actually revealed the name of my machine, but this is a prototype I worked on last year for this process called the Despacito, the Dynamic Electric Sustenance Packaging Apparatus Enclosing Instrument via Thermal Operations. So it has 6 main features: the ingredient hoppers, the electronics, the ingredient feeders, the control panel, the sealer, and the bag loader. So let's take a closer look at how it works. So these are the main components. We have the ingredient feeders and the bag loader. So it uses 3 kinds of motors, which are servo motors for the claws, stepper motors to control the axes of the bag loader, and a DC motor for the ingredient feeder. Now, the reason I'm using various kinds of motors is that servo motors have direct position feedback. So they're great for things like claws to hold bags, because they can be set to either open or close very easily. They have a limited range of motion, but they don't need that motion, which is why I'm using them. Now, stepper motors are similar to servo motors, except they can spin continuously, but they also have position feedback. So they can be stepped to a certain position, hence their name. And DC motors just spin continuously when you give them a power input, but they're also a lot stronger than the servos or stepper motors I'm using, which is why I'm using them for the ingredient feeders. Now, if we take a closer look at a cross section of one of these, see it has a reservoir in the middle that the ingredients from the hoppers will fall down into. Then here's a crude animation. It will move forwards until the ingredients fall out the bottom into the bag. So if we want to take a closer look at the bag loader that will hold the bags, the bags are held in these claws here. So you can see it can hold 2 at once. Using this rack and pinion gear, it can open and close the bags, and the whole thing can rotate about its middle axis, as well as move this up and down to move it to the funnel or the sealer. So these are the electronics that the past version ran off of. We have just very cheap stepper motor drivers that take the inputs from the Arduino Mega that I'm using and convert it to a electrical waveform that the step motors can use and output motion from. We also have single pole, single throw relays, which were used for the DC motors. This is a DC motors run off of a much higher voltage than the microcontroller can output. So we had to add those as an interface so we weren't short-circuiting anything or overloading anything. And this is also the control panel input, so various settings could be changed. Now for the version I'm making, I want to upgrade it. And one of those is adding a double pole, double throw relay with 2 transistors. And the reason I'm doing this is because the past version just used an auger system that I'm changing out for that other system because the auger system was very slow and had a tendency to jam. And the advantage of this relay is that the motor can be moved back and forth in both directions, which is what we need for that system. And I also plan to add limit switches to monitor the position of all the motors, plan to upgrade the stepper motor drivers, and I'm also going to add a Raspberry Pi to host custom G-code firmware. So what is G-code? G-code is a machine language which is used for various manufacturing processes, such as 3D printing. Here, a 3D mesh is converted into a G-code file, which is an alphanumeric file containing all these numbers and letters that a printer's control board can read and output it as a series of motor movements. So here's what my circuit will look like. We have the main Arduino controlling all the motors, and it will interface via serial with the Raspberry Pi, which is hosting the G-code firmware, which takes the series of instructions that you want the machine to output as a series of instructions that the motors can read. So to recap, this is the main process. We have the ingredient loaders, which take it to the bag holder. It is sealed automatically by the machine. It goes on a conveyor belt where the bag is weighed and checked to make sure the weight is in the right tolerance, and then it is packaged into a cardboard box. So how is it going to be food safe, since this machine is going to be in contact with a lot of food? That's its entire job. So I'm going to print it out of polyethylene terephthalate glycol, also known as PETG. And I'm going to use a stainless steel nozzle instead of a traditional brass nozzle so that there's no risk of lead being transferred into the parts. And the advantage of PETG, it's also a very strong and resistant filament, and it's already widespread in the 3D printing community. And it's also the kind of plastic that water bottles are made out of. So we already know it's food safe. And any other parts? So there's actually one problem with the 3D printing process. And that's if you look closely, these are the layers of the 3D print. Zoom in very far. They have these little gaps where the layers are. And bacteria can accumulate in those gaps, which makes it a problem for sanitizing because you can't get those bacteria. It causes problems, causes infections, and you don't want that. So there's a simple solution to this process, and that is just sanding the parts flat. And that way there's no gaps for bacteria. So that process will have to be made sure to be done very thoroughly on all the parts so that they can be sanitized. And all other parts in contact with food will be made out of 6061 aluminum, also known as the aluminum used in beverage cans. So again, we know that's food safe. It's already used in the food and beverage industry. Everything will be lubricated with a food safe lubricant. And for additional safety, everything will have fuses, all the motors, and of course an emergency stop button in case of emergencies. So if you compare these side by side, for 8,000 meals and a team of 11 volunteers, the volunteers will take about 8.4 man hours, whereas my machine will take only about 3, which is about 27 times as efficient. So another advantage of this machine will be completely open source so that other people can add upgrades to it. They can figure out how it works. They can implement it for themselves. And if you remember how I said it's programmed off G code, that's a very adaptable system. So you can put your own tools, such as a 3D printer extruder, onto the end and essentially turn it into a 3D printer. So it also has a variety of uses in industrial engineering for packaging and other assembly applications. And that is the end of my presentation.
Good job, Joey. That was fantastic. Does anybody have any questions?
Yeah, are you doing the conveyor? Are you building the conveyor belt as well, or are you going to get a commercial off-the-shelf one?
I was going to reach out to a few companies. So I know there are actually some headquartered in St. Louis that specialize in that kind of stuff. So I thought I might be able to reach out to them and get one maybe discounted.
I also had a question about the process. If I remember right, which there's a chance I'm just wrong here, but you said the bag is sealed and then weighed. So what happens if like the weight is off? Do you have to like puncture the seal and then reseal it?
Well, my philosophy is that those reservoirs that all the food is contained in are like exactly 8 ounces, which is the exact amount that you want the rice to be. So that's mostly like if there was a problem, it would just reject that bag. I also plan to have like systems in place, like if it rejects like 3 bags in a row, it'll like automatically stop the machine and you can see if something's going on. But they should weigh 14 ounces. Normally, that's just like a form of quality control. It was actually recommended to me by an MIT professor, so I decided I should implement that.
Awesome. Any further questions? If not, then we'll move on to Cael. Thank you, Joey.
Okay, can you guys see my screen? Can
Yes.
Okay.
Yes.
Okay, so hi, my name is Cael Magner, and so my Think presentation is called "Here Will Not Come the Sun," which is a reference to the Beatles song "Here Comes the Sun," and it is a real-time sunscreen imaging system intended for use in institutional and commercial environments. So that essentially just means that it's a detector that you will be able to walk by, and it will tell you where on your body sunscreen is applied. So before getting into it, I want to just establish why that's important. So everybody, regardless of skin tone, can be at risk for skin cancer, particularly skin cancer caused by the sun. And even in people who are due to darker skin, higher melanin content, are statistically less likely to develop skin cancer. Long amounts of sun exposure can lead to faster aging, dark, weird spots on the skin, stuff of that nature. And if they do happen to develop sun-caused skin cancer, the detection rates are much lower until much later. And as a result of that, the FDA and the American Academy of Dermatology recommend that everybody wears sunscreen, regardless of who they are. And the other application is in countries like Australia. This is just a brief excerpt of a slide from the Western Australian Sun's solar policy. And as you can see, it's quite intensive. They require hats, during the daytime. They will literally cancel events if it's too sunny outside. And another thing they do is, particularly for the younger kids, they screen every single one of them every day before they go outside to make sure that they have properly applied sunscreen, particularly as on different parts of your face, you actually can significantly increase your risk of sun-caused skin cancers by missing certain regions like this part of your nose, below your eyes, etc. And this is just a quote from the FDA. Everybody needs to wear sunscreen. Although one thing I do want to establish is that there is no direct link between climate change itself and skin cancer. Thankfully, due to the Montreal Protocol in 1989, we banned a lot of ozone depletion substances. And so the amount of UV radiation as a result of that has not increased. But changes in human behavior due to warmer weather, spending more time outside, overexposure, that can still be a risk for skin cancer. So just some use cases I came up with. So K through 12 schools in the United States, there's programs in states, Western states like Nevada, that place sunscreen dispensers all over the school. So this logically complements that. Beaches, schools in other countries, and workplace exposure. A lot of the Western states and other countries, particularly desert countries, have laws that restrict how long employees can be outside when it's very sunny. And this complements safety around that area too. So what I've came up with for this is essentially a system. I was heavily inspired by the very ubiquitous infrared temperature checkers. I don't know if you guys have ever used one. It's you walk up to it, you stay there for about a second, and it tells you what your temperature is. So this is like that, but instead of telling you your temperature, it tells you where on your body sunscreen is. So a couple of the different components are, you have the 3-camera system. 2 of the cameras are in the UV spectrum, and I'll cover why that is in a minute. And then a color camera, which the result of which will be overlaid onto, so that it's visible on a color image. And that is for contrast purposes and to ensure that even people with worse vision are still able to see it. And then I also have a UV index sensor, as this whole operation, to save money and to keep it in budget, will use the sun as an illumination source. So it will not work without the presence of the sun. And in order to make sure it automatically shuts off, I have the sensor, as well as a little encoder where the overlay color can be changed. And then on the left, I just have a very early sketch of what I was planning on doing. Okay, so how does this work? So this is used as a technique called differential spectroscopy. And I know that sounds like, oh my God, but all that is that you're essentially looking for regions of change to identify a substance. So as you can see in the 3 charts, this one, and this one, are of different sunscreens with different percentage of active ingredients. And they all do not react. They all reflect little light, so they appear very dark below about 375 or so nanometers. And then after that, they all cut on very significantly, where they begin to reflect a lot more light, and they would be observed to be quite a bit whiter as a pixel. And then over here, I have a chart of different groups of human skin, although that's really a misnomer, as there are plenty of people who exist in between these groups and would be on the margins. So the problem with just taking a regular UV camera at yourself to image sunscreen is that if you have darker skin and you're looking at about 350, where the sunscreen would be dark and easy to see, it does not contrast very well with your skin. And that's problematic for reasons I established earlier, which is that everybody needs to wear sunscreen, yet a traditional just sticking a camera on yourself would not work in this situation. So instead, I'm going to do differential spectroscopy, where you examine where the sunscreen is cut on, so about 450 for all of them, and you also examine where it is not cut on, about 350. And because you know these wavelengths and you compare the two, it exists as essentially a region of difference between the two. Whereas this substance, skin, as kind of a control, does not experience as much shift and would not show up on a difference between the two. I mean, there is about a 10% difference here, but that can be filtered through image processing. So in order to do that, you need to have a camera that's capable of imaging UV. And this is actually particularly challenging, as UV cameras, particularly the high-end scientific ones, can easily go for over $10,000, which is not practical for both commercial applications and is well outside this project's budget. So to get around that, I'm just using standard low-cost robotics imaging cameras, which are monochrome, which means that they lack any sort of filter that restricts them to visible light. And in addition to that, they have enough of a property called quantum efficiency, which means that the electrons at the energy level of UV light will penetrate the image sensor and show up on an image. So this crazy diagram, I'm not gonna try to talk over this. I do have examples, but this was the image proposal processing pipeline that I submitted, but it's not really a fun looking diagram, and it would be very boring to talk over. So instead, I've actually brought some of the pictures from the software that I used to create this algorithm that I included here to just show how it works. So in order to compare between the two images, you need to have two images taken of the exact same location in different wavelengths. And so usually this is accomplished with a prism, but the problem with a commercial application is that to mount a prism on this thing and still have people walk by it and it's bulky, that would not work out very well. So instead, I'm going to approximate it with stereo cameras. So the first step to approximating the two images with stereo cameras is to align them in one of the axes. And this is accomplished through a very common technique called stereo rectification, where you essentially say, okay, given these two cameras, I'm going to try to approximate them so that the y axes are the same. And this is, I'm not going to get too deep into this because it's pretty common, but this is accomplished using something called Zhang's method, where you develop knowledge of the rotation between the two cameras as well as the translation. And then from there, you can pass it to a function, and it takes your two images as input, and it ensures, based on knowledge of an object with a known reference, in my case, the chessboard, it aligns them in these two axes. But as you will notice, they're still not aligned in the x-axis, as evidenced by the shift between these two. So from there, you take traditional image registration, which is essentially saying, I want to align these two images, period. And that will align them in the x-axis. You can do image registration in both axes, but I found that through experimentation, that was less reliable. It's also important to note that image registration will look at the contents of the image, whereas stereo rectification uses parameters already known about the camera that are external to the image. And that's actually really important, as doing this as a real-time system, you need to have consistent performance between frames. With image registration, where it's looking at features of the image, it will vary between frames because it's looking at the features. If they look different per frame, it may try to align it a little bit differently, and that's not going to work. So the next step is to pull the transformations that create these aligned images out of the registration process and apply those indiscriminately per frame to ensure that you're getting consistent alignment results. And I know that's a wordful, so I made a little diagram just to illustrate that, what I meant by that. So in a traditional image registration technique, you can imagine camera one has this 3-dot, and this is a simplification, this 3-dot thing, and then camera two has the same thing, but maybe slightly further to the right because it's slightly moved over in space. So a traditional image registration would take these two, notice the red line, and then just align them, and that would be your final result. You would have no knowledge of how that process worked. So in my case, I actually don't want to do that because it would vary between frames. So instead, I want to pull the transformation, in this case, y equals x plus 1, out of that registration process, and then I can apply that to every frame, regardless of the frame's content. So if I had a different image here where the image registration algorithm was unable to align it, I could still use this transformation and get the same results because the cameras haven't shifted to each other in space. And and then from there, I'm going to subtract the two images, and essentially from the mask, which is the difference between the two images, I'm going to project that onto a color image of the final result. And that's going to be what's seen by the end user instead of either a black and white monochrome image of themselves on a UV camera, or just the difference between the two images, which is a black image with just a couple white pixels. And then that's going to be shown on the monitor. So in order to make this a portable system, I'm designing just simple mounts that allow me to include the project single board computer, which is a kind of an off-brand Raspberry Pi with a very beefed up graphics processor because I'm trying to hit a performance target of about 30 frames per second. And this is the mount I came up with. This slips in between the VESA plate, which is just the 4 screws in the back of the monitor. And it includes standoffs that allow me to include the computer on the back so that this can function as a self-contained unit. And then I've also been designing the camera mount. So this will accommodate the 3 different cameras required to perform this project, the 2 UV cameras and the color camera. And then lastly, I just want to talk about some external use cases for this. So this technique, this differential spectroscopy, can be applied to pretty much anything, as long as you know that the reflectance chart of both the material you're trying to image and the materials that you're trying to compare it against. So, and doing it with stereo cameras instead of mounting a whole prism, I feel at least, really reduces the barrier to entry. So this also proves the viability of this for other use cases, particularly I run a first check challenge team for detection of materials in robotics. And yeah, that is my presentation. Any questions?
Excellent job. Thank you so much, Cael. If there are no questions, well, congrats on a very clear presentation. And Thomas and Nicholas, I believe you guys are up next.
Okay, you can see it, right?
Yes.
Okay, so our project is the deployment of autonomous micro drone swarms to save lives through 3D reconstructions of destroyed buildings in post-disaster response. And basically what that means is we're gonna send in a swarm of drones to partially destroyed buildings, and it's gonna map out the environment and send that to search and rescue people. Yeah, so the problem, the rate of natural disasters is increasing dramatically due to factors like climate change and stuff. And current human search and rescue is inefficient, mainly because of lack of information. I mean, the people are going into these post-disaster scenarios pretty much completely blind and just trying to find everyone they can in oftentimes large cities. Yeah, and so when it comes to search and rescue, time is of the essence because the rate of the survival rate of people stuck inside buildings decreases exponentially over time. So like in the first 8 hours is the most essential. After that, they don't have a good chance of surviving. And here's just a graph of the rate of natural disasters from 1970 to 2019. Specifically, we're going to be addressing going into semi-collapsed buildings and yeah, there's an example of a collapsed building.
Yeah, so what we're looking to do is try to find a way to create a inexpensive, safe, and effective solution. Because as Nick stated, volunteer search parties it's kind of rushed, the whole process, and also it's just a matter of just finding the finding survivors in a way that may not be as organized as it could be, and it's also hard to put together a team of volunteers. So many have researched the use of a decentralized autonomous drone swarm that help identify survivors. So what's good about autonomous drone swarms? Well, autonomous drone swarms are able to cover areas extremely quickly in a way that is maximizes each and every component of the swarm. So specifically, in a decentralized, there are two types of drone swarms or swarms in general. There are centralized swarms and decentralized swarms. So in a centralized swarm, you normally have like one command, like control area, that control station that sends commands to each of the other drones. And this centralized system means that one sole system is responsible for the control of the entire swarm. In a decentralized swarm system, however, that will be using the emergent properties of each and every small drone in the system. So basically each drone has a behavior that it follows. And as a result of each individual drone's individual behaviors, a beautiful pattern of just like navigating extremely efficiently will emerge from these behaviors. So when we're inside the building, current work has addressed using decentralized swarms of microdrones to locate survivors within the building. So basically what microdrones are special at is that they're able to fit through tight spaces that rather large drones are unable to fit through. So that's an advantage of microdrones. And these swarms of microdrones are able to cover the area in the building. So if they are able to provide a map of the building, that will be crucial to improving the awareness of the post-disaster response. So current work has utilized centralized systems, such as just having a centralized system to path plan, and we'll cover why those approaches are limited. So basically in that picture, this is just a simulation of drones covering a large area. So basically this is like an overhead view of a city. So we have like 50, each blue dot you can see is a drone, and they're gonna cover this area and go to the buildings. And inside these buildings, you see the red blocks with like black dots in them. Those are survivors. And each drone is gonna go through and just, I guess, locate these survivors. And here's just an example of a drone swarm where we have many drones. And so basically in one proposed experiment, we've seen these drone swarms, they navigate through the building, controlled. These lines represent the path planning system that the centralized system runs them through, and they go through the building and map the building out. So there are many limitations with a lot of this current work. So current centralized path planning approaches, yeah, as I said, as I showed in the previous slide, they're able to map in simulation, but centralized path planning approaches are far too computationally heavy for microdrones, and they also rely heavily on GPS data, which is not accessible in a post-disaster scenario. So in the context of the previous image I just showed, that is possible in simulation because they're using drones that aren't microdrones, so they have the computational power to potentially perform SLAM, which the mapping algorithm will be using. And but another limitation of current work is that decentralized path planning approaches have not been used to actually map. So basically, as we see here in this picture, these are micro drones. And in this experiment run by a research group in Switzerland, they basically just sent these micro drones out to map in a decentralized manner. So each drone followed its own behavior. Or no, they didn't map, sorry. They just were supposed to cover a large area. And we're looking to kind of build upon this approach by having a swarm of our micro drones be deployed by a separate drone. And then these micro drones will eventually map out a building to build upon this approach that covers the building.
Yeah, so as Thomas kind of touched on, our solution is a control drone / micro drone system. So first, the control drone is basically just a larger and powerful, computationally more powerful drone capable of running the mapping algorithms that we need. And the micro drone are small 10-centimeter crazy fly drones. The micro drones are going to be deployed into the building, and they're using swarm gradient bug algorithm for path planning. The control drone is the beacon. So like in the swarm gradient bug algorithm, in order to find their way back, because they don't have any GPS, they just use the control drone as the beacon. And a swarm gradient bug algorithm is basically like a wall path planning or a wall following algorithm. So that's how they navigate. And then when they're finished, they'll all go back to the control drone. And for SLAM for SLAM, the micro drones are going to send odometrical and visual data to the control drone. Odometrical data is basically like how far you've traveled in like a certain amount of time. So like I traveled like 10 meters in like 2 seconds. So you can tell how fast you're going and your position relative to where you were before. And this is useful because there's no GPS. And it also sends the visual data for the 3D mapping. And so the control drone would be located at the entrance of the building, and it receives data from the micro drones that I mentioned before, and uses multi-robot large-scale direct simultaneous localization and mapping. That's the algorithm it'll use to map. And basically, large-scale direct basically just means that there's no sense of scale. And so it can really, like, the environment that it maps can be like super small or super big. And direct just means it directly uses the image. Some SLAM algorithms take features from the image, like corners and stuff, to sort of simplify the image and make it less computationally intensive. But we don't need to do that since we're using our control drone for the SLAM process. So we use a direct algorithm, and simultaneous localization and mapping is just, since there's no GPS, it localizes itself within the environment and creates a 3D map. And then after all the mapping is done, the micro drones return to the control drone. And this is just an example of what a control drone would be. And here's a graphic on what it would sort of look like. So for the swarm gradient bug algorithm, you can see here's the control drone, and then there's the 3 micro drones, and they're just gonna go around the building using SGBA. And then while that's happening, the micro drones are gonna be sending image data to the control drone, image data and odometrical data to the control drone. And then that's gonna be creating individual maps for each of the drones. And then when it detects an overlap in the maps, when it detects an overlap in the maps, it'll then combine those 2 maps that it finds. So then it'll be able to have just one big map for the whole environment. And that's how we're gonna do the multi-robot part.
Yeah, and for we go back this time. So for our swarm gradient bug algorithm, basically this algorithm is gonna have each drone go off in like a random direction, and each drone, even though it doesn't know exactly where the other drones are, it has access using one of the attachments that will attach onto the Crazy Fly drone. It will be able to have access to a odometrical sensor. So basically, it will be able to kind of detect when the other drones are nearby, which allows it to know what spaces to go to and which spaces not to go to. So yeah, they will continue to follow the walls, and when they get near another drone, the swarm gradient bug algorithm will essentially just have make a decision to which drone will go in which direction, to avoid any overlap within the algorithm.
Okay, so our approach, we're basically going to test like the smallest micro drone control drone system that makes sense for our budget, or the biggest one that makes sense for our budget, which is 1 model control drone and 3 micro drones. And first, what we're going to do is implement swarm gradient bug algorithm in simulation. And we're going to do this using the Crazy Swarm simulation software. and SGBA is already built on GitHub. So we just have to grab it from GitHub and make any minor adjustments we need in terms of like version control and stuff like that. And then implementing multi-robot LSD SLAM. First, we're gonna do that in simulation with a regular camera. And that's LSD SLAM is also already on GitHub. So we just have to get that from GitHub and set it up with ROS and all the correct versions and stuff. And then LSD SLAM isn't built for multi-robot systems, but there's a framework that was built that helps, that allows you to convert SLAM in different SLAMs into multi-robot systems. But there's one problem with this paper. As I mentioned before, LSD SLAM is a direct SLAM algorithm. So basically it uses the full image instead of just the features. However, in the paper, in the framework, they use feature-based SLAM, which basically means we're gonna have to figure out how to implement it with the direct SLAM. And then, yeah, once we do that, we're gonna develop the multi-robot LSD SLAM. And then here's just an image of SGBA, the crazy swarm simulation software. Okay, and then, so once we implement all these in simulation, we're gonna have to put it all together. So we purchased the materials, the crate, which includes the crazy fly drones and all the attachments, like the radio and the like sensors. And then we build the model control drone. The control drone isn't actually gonna be a real drone because we don't really need it to be. That's not within the scope of this project. It's mainly just gonna be, just a model drone that doesn't actually fly with a Jetson Nano on it. The Jetson Nano is really the only like requirement for it we have. The Jetson Nano and being able to hold all the crazy fly drones on it, because Jetson Nanos are commonly used on drones. So in order to be realistic, you can't just like have a $1,000 PC running it, because that's not realistic. And then we set up a link with the control drone from the micro drones. Then we put the SGBA algorithm that we made in simulation on the micro drones. Then we implement multi-robot LSD SLAM on the control drone. And we also got to set up the camera data sending from the micro drones to the control drone. And then after that, we just test it. And here's a graph of LSD SLAM versus Orb SLAM. This is basically why we chose LSD SLAM out of all the other SLAMs, because as you can see, Orb SLAM is a feature-based SLAM algorithm, which again means it takes like corners and edges and uses that to form this point cloud map, as opposed to taking the full image. And you can see the disadvantage here is that it has way less points, even though it's faster and actually the points are a little bit more accurate. It has way less points and it doesn't create a usable map. So that's why we chose LSD SLAM.
Yeah, so our MIT Think goal is to produce a swarm system of up to 4 micro drones. And also, as I said, the control drone to map out the relatively cluttered building. So basically, we want our swarm system to cover about 70% of the algorithm and also, or 70% of the environment, and also return back to the beacon at a rate of 70%. So to measure the accuracy of our SLAM algorithm, basically we compare the generated map by the micro drones with a actual map of the building by comparing the points through a standard deviation test. And this way, if we don't have access to like an actual laser scanner that can do this, we also have thought of a way using just measuring the ratios between the buildings, between objects in the building to help create these metrics for us. And here in this picture, you could just see like, you can just picture like the drones going through the building, and also our software provides us with a coverage statistic of the environment's coverage. So basically we'll be able to see how much environment has been covered through our algorithm.
Okay, so some potential problems would be handling the various versions of software, because you know, we're grabbing a lot of different softwares from different papers, and these papers were made, and some in 2015, some in 2020, and so just setting up, like adjusting all the versions so they match with all the like Python packages and whatnot is a challenge. And then when testing drones are really fragile, so you have to be extremely careful, especially when you're first testing out your algorithm, because you don't know how it's going to translate from simulation to the real world. So you have to like start with really short tests and gradually increase the work of the drones. And then one way we can sort of test that our algorithms are working properly is using cameras, high-speed cameras, to record the drones and make sure they're moving according to the algorithm. And any questions?
Excellent job. Go ahead.
What's the battery life of the micro drones, and how do you plan to recharge them?
Yeah, so the battery life, it's like about 7 minutes. So I think our main goal is kind of just have them go through a building in about 7 minutes, and that might be kind of difficult, obviously. So in terms of recharging, we may have them just come back to the control station. Our control drone probably would have like a charging dock on it, and that's how we'll recharge, and they can maybe go back out into the building and just go around and continuous process.
I also had a question, actually. From what I know of search and rescue situations, it seems like it can be a little bit unstable at times. So like, what would happen if like one of the drones or even the control drone gets like knocked over by a falling piece of debris or something?
Well, as I said before, the drones are really fragile. So if like a brick was to just fall on one of the micro drones, it would just be destroyed. But the good thing about our solution is the Crazy Fly drones are relatively cheap and inexpensive. So they're kind of made to just like, you just get a bunch of them and throw them in there.
Yeah, and obviously it'll be better than having like a human get hit with a brick.
Yeah, $200 drone rather than a rescue worker.
Very true, yes.
No more questions?
Yeah. What sort of a tech stack do the micro drones use, and what communication protocol are you guys using for inter-micro drone and micro drone to control drone?
Yeah, so we're actually looking to use an ultra wide bandwidth solution, communicate, but also each drone comes with a crazy radio PA. So that's what they call it, the Crazy Fly drone company calls it. And basically they just, that's how they're gonna communicate to each other and to the control drone, because we'll set one up on each drone. So yeah. Also, oh wait, actually, they'll be using like a peer-to-peer communication system. So basically each drone can like talk to the other drone, send information between through the crazy radio PA, but that's handled through the attachments that their company provides.
Great. Any other questions? If not, good job. Excellent presentation. And next we will have Ojas.
All right. Hopefully everyone can see and hear as necessary.
Yes.
Yep.
Perfect. So my name is Ojas Gupta, and my project is titled Multipurpose Inexpensive Laser-Induced Breakdown Spectroscopy Device for Rapid Diagnosis of Osteoporosis. Definitely sounds like a mouthful, but once you break it down, it's not so bad. So first, let's learn more about the disease. So osteoporosis is a broad term given to the bone disease, which is caused by weakened bone architecture characterized by fractures. This is caused by lifestyle factors such as insufficient nutrition, exercise, or sunlight. And because of this, it is more prevalent in developing countries. And people who suffer from this disease suffer from chronic and fragility fractures, which cause disability and are really expensive to live with and treat. For example, it's really common for people with severe forms of osteoporosis to break their back while sneezing. So it's a very fragile, your bones just break like really easily, and it's really hard to live with. But there is good news, and the good news is that it can be effectively managed if caught early. And this includes, lifestyle changes. A couple of papers have indicated that they got effectiveness up to 75%, as well as additional pharmacological therapy. So this is, drugs and specific chemicals. So you might be thinking, well, we know how to treat it. This shouldn't be an issue, right? Unfortunately, that's not the case. And osteoporosis is still the largest bone disease in the world and is actually projected to double to 300 million cases by 2050. And it causes one fracture every 3 seconds. And US patients alone spend 17.9 billion on treating and living with osteoporosis, even though they're only a small proportion of the total amount of patients. So why is there this disconnect? If the slide will load. Okay, so the reason why there's a disconnect is because diagnosis, forget early diagnosis, but any diagnosis at all is simply really hard to get to. Now, the WHO has only approved one method for diagnosis, which is this really cool looking machine on the right called the DXA scan. However, this cool machine also comes with a hefty price tag of $45,000, which is why these machines are extremely rare in developing countries. And rates are, commonly around 1 machine per 1 million people, which is well below the rates in developed countries such as United States and the European Union. And because of this, the International Osteoporosis Foundation estimates that around 80% of cases worldwide go undiagnosed. And usually it's the other way around. So a couple of quotes that I thought were pretty interesting here. The problem is not that we don't have treatments, it's that the treatments exist, but the people who need it can't access it. There's a clear need for a more portable and affordable diagnosis to make use of the early diagnosis treatments that we have developed. And that's where my product comes in. So before we learn about the actual device, it's first important to go back to biology and learn about calcium. So calcium is the most common mineral in the body, and among other things, plays an essential role in bone quality and strength. It also serves as one of the most widely accepted biomarkers for diagnosing osteoporosis, as lower amounts of calcium in the bones is one of the significant causal factors for breaking your bones. when your body is low on calcium, thanks to the way that the body is smart enough, it is actually able to take away calcium from less important sources to keep more essential sources, such as nerve and bone function, going. And one form of this non-essential, quote unquote, source is the hair, and specifically the hair cuticle, which is the outside layer of the hair. So now the question arises, how do we determine calcium levels in this cuticle? This is where LIBS comes in. So LIBS stands for laser-induced breakdown spectroscopy, and it can be broken down into two parts. The first is laser-induced breakdown. Now, this pretty much means when you pulse a laser, it causes a sort of mini explosion, but it's very, controlled and consistent. And that's because when you pulse, a lot of energy at a substance, it just releases matter. And then the S part stands for spectroscopy, which is just collecting and analyzing the resulting spectra to make some sense of the sample. And if you can calibrate the spectrograph well enough, you're actually able to determine the exact chemical concentrations of the sample, which is how we're able to determine calcium levels. So now in terms of previous research, I wanted to talk about this one paper written by Cherney and others. So what Cherney did is they were able to validate the science behind this entire proposal, which is using LIBS technology on the hair cuticle to determine calcium levels and diagnose osteoporosis with 95% accuracy. And they also were able to establish spectral cutoffs, which will be really critical in my own project. So you can see they have, relative intensities for healthy patients, osteopenia, which is early diagnosis, and then osteoporosis. However, it still isn't perfect, and there still is room to improve this device because their device is still over $20,000, and it necessitates expensive lab equipment, so the real cost is actually a lot higher than that. And finally, it is not portable. So my addition to the current work is to make the device portable and affordable for rigorous daily use. And there's three main ways I achieve this. First is by adding a new protocol for the treatment of the hair, which gets rid of the need for any lab equipment and helps it be processed on the go. The second is by adding a 3D printed case to make the device portable instead of a one big bulky thing that just sits in a lab. And the third is by adding, and this is where it gets really scientific, and I'll go into more detail later, but innovative laser and spectral manipulation. And this is actually an amalgamation of many techniques, each of which has proved their own efficacy. Okay, so now let's go into some more details. This is the basics. This is a really crude 3D diagram. I know it doesn't look the best, but it shows you the overall shape. It's 16 by 16 by 25 centimeters, so it fits, sticks out from your hand a little bit, and it has a sort of pyramid shape on the top, and that's actually where the laser will come out. And some other features about the device is that it has a 10-hour battery life, and it displays the percent on the top, which is indicated by the white sphere. It will also have an on and off switch and can be charged using standard USB-C cable. Within the device itself, there's an Arduino control, and it also has Arduino communication via Bluetooth for live analysis and detailed spectral analysis. So here's the device in a little bit more detail. If you open the hood, you can see that there's a laser, obviously, which releases the laser. And then it's manipulated a little bit on the bottom using Gaussian focusing lenses and other filters. And then the sample is placed at the apex of the pyramid all the way on the right. And then finally, the emission is analyzed and focused and filtered. And there's also a grading, and it reaches the spectroscopy chip, which converts the photon and other matter into electrical communication, which is then sent to the Arduino chip and sent to the computer for analysis. There also is an exhaust fan in the back on the left side. So I've also built a crude prototype at home using household materials. This was mainly to demonstrate understanding of the concepts and does not nearly serve final purpose. So I use household materials such as CDs, Legos, a magnifying glass instead of an actual focusing lens, which is why the lens had to be placed so much further from the actual camera. And there was a detectable signal, as you can see in the graph on the bottom left. And that is compared to the graph on the bottom right, which is the actual formal diagnosis or live spectral analysis using the $50,000 calibrated lab equipment. So even using these cheap household materials, we were able to, or I was able to get somewhat of a signal, but the final device is going to upgrade these components and fine tune this accuracy. So in terms of what I've already done on the project on the left side, so I have performed my device calculations and component requirements. I found all the links to the suppliers and made sure that the budget is under $1,000. So some of the more, lab what's the word? Like lab level equipments that I've found are like a 10 megawatts laser, 532 nanometers, as well as calibrated and technical lenses, formal filters, accurate grading, as well as a Bluetooth chip for operation. But the biggest thing that I have not done yet is finalize the internal 3D CAD design to hold all the components in place. And this is really important because the device will need to hold everything down to like the centimeter spot, so it can't like wiggle around or anything. And it also needs to have some sort of adjustability to allow for fine tuning in the design process. So now let's go into some risks about the project. Okay, so the first risk can be classified as a laser delivery. And this is the bottom half of the layout as shown in the image. And this is pretty much, can the laser create a plasma on the hair? So in case a plasma isn't able to be created, I've brainstormed a couple of solutions. The first is to try different sample preparation of the hair. So this includes, different chemicals, different methods of tying the hair. And another solution that I could explore is using more powerful lenses or lasers, but these do come with a cost trade-off. And the second half of the problem is signal interpretation. So can the plasma signal can be focused and interpreted by the computer? So in case the signal is too weak or the noise is too high, I brainstormed a couple of solutions as well. So the exhaust fan helps a lot here, but I could explore a more powerful exhaust fan in case the temperature is too high or there's too much dust within the container. And finally, just like the previous problem, I can explore some higher quality components with, once again, a trade-off in cost. But unlike the first two problems, this problem is really the hardest because the first two problems, there are calculations involved, so it can be predicted. But this problem simply relies on creative design. So the innovative placement and design of components within the 3D printed case is what gives this device its bulk cost efficiency. So components need to be held in place down to like the centimeter, and there needs to be predictable adjustability for fine tuning if necessary. So for example, something that I brainstormed is like, there's a little knob on the side and you can like turn it and it moves 1 centimeter closer towards the entrance or something like that. So some sort of mechanism to move around the pieces inside just for calibration purposes will need to be brainstormed. And this is the biggest task left I have to creating my design. Now for my goals on the project. For my testing metrics, I want to test the device's ability to measure calcium levels. So I have, you can test it on pure calcium pills or the calcium vitamin supplements that I'm sure we all have in our houses. And I also plan on using my own hair to see if the machine can actually determine calcium levels of myself. And my end goal is to get within 5% accuracy on the intensity readings as calibrated towards the chart from Cherney. And I've also brainstormed a possible clinical sample protocol. So because hair, like gathering hair, is relatively non-invasive and a simple collection process, it is actually possible for this device to get clinical samples and validate their diagnosis. So this is, I'm talking about real hair samples from real osteoporosis patients. And these patients would likely be sourced from a radiology center to compare this device to a current DEXA scan. And I would like to validate diagnosis similar to Cherney et al. So I can see how accurate is this device at not only predicting calcium levels, but the final end goal of predicting osteoporosis. And once again, this isn't required, but this would be a really cool way to test the limits and extents of my device. And that's it. Thank you for listening. Any questions?
All right, well, I just Googled a 10 megawatt laser, and all the responses are like the US Navy blowing airplanes out of the sky with these massive lasers. So I'm wondering, like, where are you getting a like handheld 10 megawatt laser, and like, are there any safety protocols you have to use for it?
So yeah, safety is definitely the biggest concern here. In terms of sourcing, it's not too bad because the voltage and amperes can change. So I've actually found one on Edmund Optics, which is one of the top leading optics sources in America. So I have the laser, but you are correct in determining that there is some sort of safety precaution that I will need to take. I personally will need to wear glasses and have it in a safe controlled environment, but in the final device, once the device is calibrated, there will actually be no need for a safety protocol because the laser will never actually be exposed to the outside world. But because when I need to, design the device and actually make sure that the laser is going in the right spot and all of that stuff, it's definitely makes sense for me to have this proper safety protocol. Luckily, all that means is working in a safe environment where there are not any mirrors or reflective substances, as well as having the proper glasses to protect from eye damage.
Awesome. Any more questions for Ojas? If not, congratulations and thank you so much for your presentation. Okay, next we have Jessica and Christine.
Okay, can everyone see that?
Yes.
Okay. So hi, I'm Christine and I'm a junior at South Brunswick High School in New Jersey.
And my name is Jessica and I'm a junior at MMI in Pennsylvania. And today we're proposing a new design for a lumbar disc implant to tackle the effects of degenerative disc disease, or DDD for short, which is the natural wearing of one spinal disc that comes with aging. There are a lot of surgical techniques that are currently being used, one being spinal fusion, where someone permanently connects the vertebrae so they heal together, but this eliminates motion between them. So to avoid spinal fusion, another method of combating DDD are lumbar disc replacements, or LDRs, where they replace a degenerated disc with an artificial one. However, current LDRs carry many complications for two primary reasons. Current LDRs are not customizable for sizing, which often leads to dislodging, loosening, fracture, or increased pain. And as for material and design choices, these often lead to a lack of mobility, increased wear, instability, and this leads to a longer fusion time with the vertebrae. And all of these factors constitute the 17.6% of patients who needed subsequent spinal surgery after undergoing LDRs originally. And it's important to note for people with other health conditions such as diabetes, they have a much higher complication rate. Diabetes has been associated with infection, non-union, and less favorable outcomes after lumbar spine procedures. And there are two current FDA-approved LDRs on the market, the ActiveL disc and the ProDisc-L. The first is the ActiveL disc at the top, but they only have a success rate with a full range of mobility at 50%. And for the ProDisc-L, it's a ball and socket model, which causes unnatural mobility, more wear, and provides no shock absorption. And both possess problems with material and sizing. Sizing is always a concern because they only have limited size options and they're not customizable. And both use cobalt chromium, which has a Young's modulus much higher than bone. And this essentially means that it's much more stiff than bone and doesn't match as well with the bone stiffness. And it's important to note that these are both generally successful, they're FDA approved, but they're not as successful for people with other risk factors such as diabetes. And this is the main problem that we're aiming to tackle with our implant.
So in the past, researchers at Brigham Young University, they've like kind of explored using origami in medical devices to make implants minimally invasive. But as we were doing research, we were unable to find like further developments in these areas or like other research that they have done to like further that idea. But as for the materials that we're using, porous titanium has been explored to promote better osseointegration, which basically just refers to the connection between the natural bone and the surface of the implant. Polyurethane, which we're going to be using for the actual origami part of the implant, it has been used in many medical devices because of its strength, elasticity, and also its high biocompatibility. And currently, like researchers are testing different coatings just to optimize osseointegration and preventing infection in titanium implants in general. And so our implant incorporates Kresling origami, and this type of origami structure has been used in a lot of different robotics applications. And researchers have been able to directly 3D print the structure and demonstrate its mechanical benefits as shown here. But Kresling origami structures haven't been explored in the medical context, which is what we are doing through our project. So as for our solution, we are basically just combining elements that have been previously like researched and proven into a wholly like unique perspective and application for lumbar disc replacement that will be especially beneficial to people with underlying conditions such as diabetes. And as you can see from the diagram, we're using porous titanium end plates with keels to allow the implant to be stably fixed to the surrounding vertebrae. And the end plates will also have a bioactive coating to prevent infection and also encourage bone growth and osseointegration. We also have a polyurethane Kresling origami insert, which would allow for natural mobility, shock absorption, and stability. And we're also including a polyurethane spring core that fits in the middle of the origami just to establish a minimum height for the implant so the implant doesn't completely flatten. And within our design, there aren't any like articulating parts that are exposed to like outside, and that just serves to reduce the risk of wear particles, which can cause a lot of different complications inside the body. So this first image here is the same as the previous one, and it just shows the separate parts of the lumbar disc replacement that I discussed on the slide before. And when fully assembled, you can see like it just flattens down to create like a more traditional lumbar disc replacement look. And if you look at the cross sections, to allow the origami insert to like attach to the end plates are going to contain a groove just surrounding the perimeter. And the insert is gonna be specifically designed to latch into the groove, basically allowing for mechanical adhesion to the end plates. And as I said before, the core is just gonna fit inside the Kresling structure. So these are a few pictures of the CAD modeling for the end plates. The first one is just an overhead view just to show like the footprint and the shape for the implant. The third picture is just a design for fitting the spring core into the end plate. We're all using like, we're just gonna be using like mechanical adhesion, not like chemical bonding methods. So it's gonna there's gonna be like a expanded section on the bottom of the core just so it could fit into that like groove there. And this is a mechanical adhesion model for the origami insert. And you can see that like the groove running here is what the insert will fit into. So we're planning to use chitosan and bioactive glass-based coatings with BMP2 and vancomycin. So just to break down these components, chitosan is widely used. It's a widely studied biomaterial that's used to promote osseointegration, and it can also control the release of drugs. So like vancomycin, which we're using, which is an antibiotic. Bioactive glass is commonly used in coatings to help the implant attach to the surrounding bone, and BMP2 is a growth factor that will help the bone form a 3D interlocking bond within the pores of the titanium end plates. And we're going to be following, for coating it, we're going to be following a similar method to the one shown in the diagram here, which is already like thoroughly outlined in previous research.
For the origami itself, we're using a Kresling origami pattern, which is shown in figure A to the side. Kresling origami is flat fold, meaning it's a piece of origami that can be pressed all the way down and recoil back to its original shape without altering the structure. And you can see this in figure V. So when inserted in the patient's spine, it can expand to fit perfectly between the patient's spinal discs. And because of the natural structure of the origami itself, it will be able to match the angles and spacing. And as for measurements, fully compressed, the disc is about 7 millimeters. And with the core inserted within it, the entire implant ranges from 8.5 to 15 millimeters and of an angle up to 20 degrees. For our current progress, what we've done over the past few weeks has been gathering data on the mechanical properties of FDA approved LDRs and industry standards to ensure that we meet these. And with this new information, we're working on modeling the end plates and 3D modeling. And we're also currently working on testing variations of the Kresling origami pattern to make sure that we have the optimized structure and function. And you can see that there are various versions to the side. As for goals and measures of success, we have 4 primary checkpoints. The first is going to take place throughout the rest of February, which is confirming our design feasibility and making any improvements while 3D modeling, where then we want to move into March, where we're going to finish printing and assemble the implant. And then in April, we're going to primarily focus on testing. And because ours is primarily biomedical engineering, we're going to need to focus on mechanical and biological testing, such as a different type of live dead assays or cyclic load testing. And our end goal is to interpret the test results and compile a paper comparing our implant with the current FDA and marketed implants, such as the Active-L and ProDisc-L that I previously discussed.
Yeah, so just to add on, we don't really expect to like surpass these FDA approved lumbar disc replacements given the timeline. But we are trying to emphasize like new methods and qualities of our lumbar disc replacement, such as the origami or the coating, so that it can be further explored for future biomedical applications. And this is just a list of 3 possible obstacles that we might encounter. And then we also listed our mitigation strategies off to the side. So firstly, we are a bit unsure of how to model the origami so that like it can be directly printed without having to be folded, and as well as the porous titanium. But we know that this is possible since it has been done before. We found a bunch of research papers that kind of detailed it. And this is mainly going to be an area that we would need like mentorship in. Other obstacles are just like implant durability and the effectiveness of the coating, but these both can be improved by further testing and making adjustments to our design, such as altering the concentrations of the compounds that we're using in the solutions. Yeah, so overall, our lumbar disc replacement is a unique approach to combat the effects of degenerative disc disease, and this will hopefully introduce a new angle to biomedical applications in the future. Yeah, so thank you so much for listening. And does anyone have any questions?
Yeah, so I know you guys are going to put an antibiotic on it. So I was just curious if you were going to do any like swabbing and then plating to see if there was any bacteria developing on your implant. Because I know with 3D printing, I think Joey brought this up with the little layer lines being like hotspots for bacteria. If there was anything being done to mitigate that potentially?
Yeah, I'll kind of touch on this. As we kind of mentioned, our third checkpoint is primarily the testing, and we were planning to do testing just on all the biomaterials and all of its properties just to make sure we're doing it properly. And obviously, because we're going to be making a report kind of comparing it to the current ones. So that's definitely something we're including in the biological testing aspect of our design.
And also to add on to that, how are you planning on 3D printing it?
Yeah, so after we finish like modeling and everywhere, there's like some services online that like we include this in our budget as well, that like you can print porous titanium, and you can also print like the polyurethane elastomers that are like typically used in biomedical applications and implants.
I actually had a question about the design. So will it be like one size fits all, or like the actual like plates itself, will there be different sizes depending on the patient? Like, is that customized or just general?
Yeah, so we're just like for testing and like all those purposes, we're just going to be using one size. But in like current lumbar disc replacements, and what we're planning on doing is like the end plates are going to have to be like customized just to fit each person's body. But the actual like origami insert, like that, it can be like based on the core in the middle, it can be adjusted to like all the different like variations in size between like 8.5 millimeters and I think 15 millimeters. So that like it doesn't have to be reprinted each time. It just depends on the size of the core we use in the middle.
Very cool.
I was just wondering, like, what was your inspiration for this project?
I think it was kind of a combination of our interests. Like, I'm really interested in origami, and then Christine's really interested in kind of biology, like biochemistry. And when we started talking more into it, we were trying to find kind of a purpose that we could connect it to. And one of the main things is degenerative disc disease is mainly from aging. And like, it's not really an explored region because a lot of people think, oh, it comes with aging, it's going to happen to everyone. But for that same kind of reason, we kind of want to tackle it because it happens to everyone and it leads to a lot of increased amount of pain that we felt like we could mitigate through implementing these new strategies.
Any other questions for Jessica and Christine? If not, then I believe, William, you have the final presentation.
Can everyone see this okay?
Yep.
Awesome. So yeah, hey everyone, my name is William Hong and I'm a current junior at Berlin High School in Nashville, Tennessee. And as you can see from the title of this presentation, my project is called Combating Diabetic Neuropathy using machine learning-based analysis of the dynamic pupillometry. And with that, let's get into the presentation. So beginning with the problem, diabetic neuropathy is a condition that unfortunately affects over 1/2 of everyone suffering from diabetes. And essentially what happens is that the high blood sugar in someone's body starts to kill off the nerves in their brain. And eventually over time, we see people suffering from extreme pain to paralyzation of their motor skills. And this essentially renders the victim disabled because as more and more of their nerves start dying, they can't move their legs, they can't move their feet, they can't move their hands, etc., etc. And you can see one example here on the right of the terrible outcomes of diabetic neuropathy on the feet, for example. And as of now, there currently is no cure for this disease or condition. Now, the good news is that with early detection, we can stop the progression at its root. And if this occurs, the patient usually turns out absolutely fine. There's no paralyzation, no immobility, and no negative effects because we're able to identify the root cause. And although there's no cure, we're able to provide the patient with treatments that actually stop the progression. Now, the bad news is that this early detection is actually extremely difficult to do successfully because diabetic neuropathy is asymptomatic in its early stages. So by the time you actually start seeing symptoms, the conditions has probably already progressed so far enough to the point that the damage is already permanent and irreversible. That's why early detection of this disease is so crucial. Now, on top of that, the current system for early detection of diabetic neuropathy is extremely underdeveloped because either A, you have super inaccurate tests that rely on subjective responses from the patient. So for example, one method involves applying pressure to the foot and then asking the patient what they feel or if they can feel that pressure. And of course, all the answers you get will be super subjective and they vary from patient to patient. So this would often lead to inaccurate diagnoses. And the second option, B, requires super expensive medical technology that many areas such as like rural hospitals, under-resourced hospitals, and developing countries probably do not have access to. So yeah, diabetic neuropathy is actually a relatively small complication if you're able to detect it early, but right now, most people simply just don't have the technology or capability for that to occur. Now, specifically on the current work being done to address this problem. So first off, there are a few early detection methods being used right now. These include tests such as the Ipswich touch test, vibration perception testing, and pressure testing. These were all the tests that I kind of was referring to in the previous slide, because for example, all of them apply a sensation stimuli, and then they ask the patient if they feel anything. So yeah, this is all the subjective tests that I was mentioning before. But on the topic of using dynamic pupillometry, specifically towards diabetic neuropathy, there have been a few pilot studies being done, and all of them have concluded that there is convincing evidence on how pupillometry, which refers to the eye, can be an accurate biomarker and predictor for diabetic neuropathy. But I'll talk more about this on the next slide. Empirically, pupillometry has already worked in diagnosing other neurological conditions, such as Alzheimer's and concussions. But the biggest problem is that all of these pilot studies, none of them actually take the next step to create an application or project that can genuinely be implemented in these hospitals to help with screening. All of them just support the idea that pupillometry is a feasible option, but none of them have actually taken the next step. So as of now, there is no tangible tool that uses pupillometry for this purpose. And hopefully my project can address that current issue. Now, previously, I have mentioned how the current problems involve inaccurate technology and expensive medical systems. So my project aims to provide a solution to both. It's a low-cost, convenient early detection system through dynamic pupillometry used as an objective biomarker rather than a subjective biomarker to early detect this condition. Now, the word pupillometry refers to the pupil's response to different stimuli, and this is the main function for the early detection project. So for example, when we shine a quick flash at a patient's eye, the increased photons from that light will cause the pupil to dilate and constrict. Now we will measure key metrics of this dynamic pupillometry, such as the amplitude of pupil constriction, as well as the velocity of pupil constriction, which will then be fed into a machine learning model called a support vector machine, or an SVM. Now, someone with diabetic neuropathy has worse neurological function because their nerves are dying, which is why their pupil would be less responsive or less sensitive to this light stimuli as compared to a healthy person without diabetic neuropathy, simply because their nerves are dying. Now, the SVM will process all of the data metrics and provide the patient with a diagnosis of the risk of having diabetic neuropathy. Now, here on this slide, it has two major diagrams of how my project will work and my overall approach towards this project. So on the left is a basic diagram of the data collection process. My project aims to be easy, accessible, and convenient. So there's no heavy equipment, no expensive equipment, none of that is necessary. It's designed to be able to be used through just a simple smartphone app. The project will utilize the phone's built-in camera and flashlight to first shine a quick 10 millisecond flash at the pupil, and then the camera can either record a 3-second video or continually take pictures of the pupil every 1/30th of a second. Now, the function of this is that it's able to capture the entire process of the pupil dilation all the way up to the point where the pupil eventually is restored to almost its original size. Now, on the right is more of like a flow chart of the actual algorithmic aspects of the project. I'll be using a free open source software called Pupil-EXT. It uses the state-of-the-art algorithms to record these metrics, such as the ones that I said before, regarding pupil dilation by performing edge detection through identifying the color contrast of the white regions of the eye, along with the colored pupil. And this software is already currently being used by countless different researchers across the globe. And the software Pupil-EXT will map this data onto a CSV file, as well as on a pupil radius versus time graph. And as you can see here on the graph, the radius would decrease with the initial flash because the pupil is constricting, but eventually it will rebound back up again. The CSV data will be fed into the SVM machine learning algorithm, as mentioned before. As of now, I'm doing two major things. So firstly, I'm looking more into the implementation of this Pupil-EXT software into my project. The software is free, it's already open source, and it's already available. So all I really need to do is to figure out how to correctly implement this piece of external software into my smartphone application. And then secondly, I'm just trying to find more data to train my algorithm. For example, I'm going to be probably reaching out to a few of these pilot studies and professors mentioned before to ask for the data set that they created to hopefully make my machine learning model more accurate with the additional data that I'm trying to collect right now. So in terms of goals, since this is meant to serve as a detection tool for disease, obviously accuracy is of utmost priority in this project. The biggest objective is to just simply create a tool that is more accurate than the current subjective measures of diabetic neuropathy. And when testing my AI, there are a few key accuracy metrics that I'll be focusing on. So first is the precision metric, which measures how many people really have this disease out of the number that I predicted. And then the recall metric measures how many people with the disease were predicted correctly. So of course, the best case scenario is for me to find a good balance between these two metrics to create the most accurate detection tool possible. But I will prioritize the recall metric more because it's unlikely for any detection system to be 100% perfect. So there obviously will be inevitably some false positives and false negatives, but it's way better to have false positives compared to false negatives. For example, if someone does not have diabetic neuropathy, but it shows up as positive, that's okay because we can do further tests to clear up the issue. But the last thing we want to do is for someone who has diabetic neuropathy to show up negative because then they never get the urgent treatment that they need. Finally, in terms of risks, the biggest one is by far the data available to train the machine learning algorithm. So since this is a very novel idea, there haven't really been many studies conducted to provide data that's like widely accessible to be used. So the algorithm might not be as powerful, but through my talks with different MIT professors this month and like a bit of research on my own, I have come up with a few solutions. So firstly, again, I'm still trying to constantly email different researchers and trying to find more data sets to be used in the training process. Secondly, one of the MIT professors informed me that as long as they use specific indicative features to train the AI, I wouldn't necessarily need to have like thousands and thousands of different data points to create the AI. My current data set of like a few hundred is enough. And then finally, he also mentioned that I can perform dimensional reduction to make my data the ideal dimensions for the research, which will also help towards solving the issue. And on top of that, I really won't be needing this data until maybe like 1 or 2 months into the future when I'm actually doing the development phase of this project. So I doubt this is a huge concern as of now. But yeah, that's then my presentation. Thank you all for listening and feel free to ask any questions.
Questions for William? All right, I guess not. In that case, thank you all finalists for very wonderful presentations. We will write a little bit of feedback and give it to you. And also these presentations will be uploaded onto YouTube, onto our MIT Think channel. So you will be able to view it there and to share it with your family and friends. This also concludes our entire trip. So I hope you guys had fun during the trip, also got something out of it. I'll be sending an email with who your mentors are and the mentorship and budget information very shortly. So keep an eye out for that. It was very lovely meeting you guys. And yeah, thank you so much for a wonderful Think 2022.